live with the back scratcher. Got one in the car, got one in each car, got one by my living room chair, got one on my headboard. Yeah, I keep them. All right, recording's going. Great, 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 great. All right, let's see. Yeah, we did arithmetic sequences last week and arithmetic series. So this week we're looking at geometric sequences, geometric series. So you definitely want to get your notes ready. Let's see, I still have my arithmetic sequence notes from last week, my arithmetic series notes from last week, and we'll add to that this week with the geometric stuff. We don't have a whole lot left. This will be a pretty quick unit starting out. We've got, oh, before I forget about it, 2 weeks from now, I'll just have a video for class because I will be out all day for the conference bowling tournament. We're getting into the season already. Conference bowling tournament is 2 weeks from today. So it's an all-day event. I won't be here at all. I'll be getting on a bus about right now. Yep, I'll be getting on a bus about now to head to Fayetteville with the teams to go to the conference bowling tournament. So just thought I'd mention that while it was on my mind, so I didn't forget. So all right, it's got a camera or two that needs to be on. Otherwise, looking good. Let's pull up what we got going in Buzz here. Let's pull up our grade screen as usual, and it shows that you should be done with the first two assignments. That was last week, arithmetic sequences, arithmetic series. See, this week we've got geometric sequences and series. Next week we're going to hit on sigma notation briefly and graphing sequences and series. So that should do well. Sigma notation, I've kind of skipped that in the past, but I've thrown it back in there because I think you need to see it, especially if you're going to go to college. It's helpful to have seen some sigma notation, be familiar with that. So I've added it back into the curriculum this year, but we'll get into that with graphing next week. So geometric sequences 5.03. Let's jump back here, open up this folder. There we go. We're going to have some class participation section just like last time. I'll open up the chat. In the following activity, you'll be shown some sequences. Sequence is a list of numbers separated by commas. Your objective is to identify the pattern and use that pattern to identify the next three numbers on the list, just like we did last week. I'm going to make that as big as I can there on the screen. Find the next three terms. Yeah, we did this last week. We're going to do it again. Different numbers. Type your answers in the spaces provided if it's a fraction and they're a decimal. So if we have this sequence where the first term is a 1, and the second term is a 4, and the third term is a 16. Ooh, you might need a calculator on this one. What is the next number? What are the next three numbers, actually? All right, Mary's already on top of this. She's got some numbers for us. Anyone agree? Give it a moment. Wait for some more numbers to appear here. Yep. We have agreements. Oh, Mary, I don't think you need your question mark. Everyone seems to be coming up with the same numbers you did. Let's see, 64. We'll try these out. This is the numbers I'm seeing over and over again. All right. Submit. Perfect. Yes, the next three terms are 64, 256, and 1024. Let's do another one. Oh, 2, -6, +18. Wow, that looks a little odd. We didn't see anything like that with arithmetic sequences. When we saw something like that last week, we said that's not an arithmetic sequence. But perhaps it could be a geometric sequence. What's going on? What's the pattern? I will say this is a geometric sequence. This is a valid sequence of numbers, and it does hold to a pattern that is very consistent. And we go over to the... If you're not sure what's going on, Don't subtract going backwards. Divide going backwards. Divide 18 by -6. Divide -6 by 2. And you should see the same number every time when you divide those. And that'll give you a clue on what to multiply by going forward. All right, Mary says it is -3. When you divide 18 divided by 6, it's -3. -6 divided 2 is -3. So this multiplies by -3 each time. 2 times -3 is -6. -6 times -3 is 18. That's absolutely correct. Absolutely correct. So knowing that, everybody, what is our next three numbers? All right. Alex is on it. We're multiplying by -3. So the next number is going to be negative then, because it was a positive 18. But then if we multiply a negative number by -3, it goes back to a positive number, right? So now we're at 162, whatever one's got. And then when you multiply that by a -3, it goes back to negative again. So with a geometric sequence, it can alternate between positive and negative numbers if it's being multiplied by a negative number every time. Negative times negative is a positive, positive times negative is a negative. Let's see. Excellent. Great work, math folks. Let's look at this one. Again, it's got all these extra dollar signs. That's just weird. But really, we got $1. We've got a $0.50. We've got a fourth of $1. So you got $1.50 and a quarter. Oh, this one doesn't say to use a decimal, so that's good. I can put it as a fraction. Thanks, Kaylee. All right. Yeah, the pattern's not that bad once you look at it. 1/2, 1/4, 1/8, 1/16, 1/32. The pattern's not bad because it's just being multiplied by a half, which means you just double the denominator each time. 1/2, 1/4, 1/8, 1/16, 1/32. Yes, that is correct. Just doubling the denominator is being multiplied by a half each time. That's perfect. All right, last one. 6, -1.2, 0.24. Yeah, I'm going to want my calculator on this to figure out what it's being multiplied by each time. I'm going to find the next three. Definitely going to want a calculator. Like I'm going to pull my calculator up there. So I have to divide going backwards to figure out what's going on here, right? So this is a 0.24 divided by -1.2. So that is -0.2 or 0.2 if you like. So let's check this first one. So if I had the -1.2 and divided it by 6, it's also -0.2. So that seems to be the consistent number that I get when I divide. So that must be the number multiplying going forward. So 0.24 times -0.2. So this one should be -0.048, according to our calculator. Then we can just continue multiplying by the -0.2, which means this one's a positive now, 0.0096 times -0.2, -0.00192. Is that right? 192? Yep, that's right. There's 192. What? Did I mess something up? So how much is each by the next term? Try again. All right, let's see if we messed up. Oh, I think there's no. I think that's right. Let's try it again. Sometimes, oh, it may be the fact that I didn't put a zero in front of the decimal, which you don't need a zero in front of a decimal. But I'm gonna check my math first. They put zeros in front of the decimal, so I'm just wondering if that's what it's looking for, because those numbers are the same. Times, oh, wrong number. 0.2. Okay, 0.24. That is 0.048 as a negative. This one's a positive. Yeah, 0.96. And this one's 0.00192. Yeah, I'm thinking it counted it wrong because I didn't put a zero in front of the decimal, which makes absolutely no sense or makes no difference. Yep, that was it. It wanted to see a zero in front of the decimal, which does not change the value of that number at all. But that was it. That was it. Let's see. Do we have another one down below? No. Okay. I'll make it smaller again. We may have another one, may not. Well, okay. So we got all of those. Notice the terms within each sequence are separated by a common multiplier. We call this the common ratio. Remember last week you called it the common difference. It was the difference when you subtract one term from the previous term. This time it's a common ratio. So they all have a common ratio of 4 with that first one that we looked at. 1, 4, 16 times 4 times 4 times 4. That was the common ratio. So this is an example of a geometric sequence. We're going to learn how can an expression or process be determined for a geometric sequence. What functions combine to create an explicit formula? And what possible restrictions exist on domains or ranges, just like we looked at last week with arithmetic. Okay, oh, we do have another exercise here. A geometric sequence is a list of numbers called terms which share a common ratio. So we're going to look at more sequences and tell me yes or no, is this a geometric sequence or is this not a geometric sequence? Okay, here we go. 4, 12, 20, 28. Yes or no, is this a geometric sequence? Remember to have a common ratio that you multiply by each time. All right. No, 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 no. I see a lot of people saying no. I'm saying, nope, this is not a geometric sequence, Mr. Brock. No. Let me see. 4, 12, 20, 20. That is a sequence of numbers and it goes up 8 each time. Oh, that's an arithmetic sequence, right? Plus 8, plus 8, plus 8. But that's not geometric. So good job. How about this one? 5, negative 15, negative 90, 270. Hmm. Nope. 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 I'm seeing some no's. People saying it's not. Well, let's see. If I divide 270 by negative 90, that's what, negative 3? If I divide negative 15 by 5, that's negative 3. If I divide negative 90 by negative 15, that's 6. It looks like this would be a geometric sequence, but they left out one of the numbers. If there was a 45 in here, that would be perfect. This would be a geometric sequence, but they left out. It was a geometric sequence, but they took out one of the numbers, and now it doesn't work anymore. Oh, I like this one. 1, 1, 2, 6. So it's like plus 0, plus 2, plus 4. You think that's a geometric sequence? You think it's not a geometric sequence? But y'all pretty negative today. All I see is no's. No, 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 no. Okay, I'm just giving you a hard time. So far, the answers have been all no, so there's a reason. So what could you multiply to get from the first term to the second term? You can only multiply it by one. That's the only way that one would equal one would be multiplied by one. Then if you multiply it by two, you can get the two. If you multiply it by three, then two turns into a six. But it can't be a geometric sequence if the multiplier, the ratio, changes every time. That is not a geometric sequence. All right, look at this one. Tell me, is this a geometric sequence? Or is this not a geometric sequence? Oh, finally we get some yeses. Yes, yes, yes. Nick Paisley even put the common ratio on there for us. It is multiplying by negative 10 each time. 7 times negative 10, negative 70 times negative 10, 700 times negative 10. Perfect. The common ratio is negative 10. About 945, 225, 1125. Does this have a common ratio? Is it consistent each time? Could we predict the next three terms if we wanted to? I'm seeing yeses. I'm seeing several yeses. Folks are saying, yeah, I believe that's pretty consistent. Because each time we're multiplying by 5. 9 times 5, 45 times 5, 225 times 5. Yep, that works. So 1126. There's a pattern times 1 times 2 times 3, but it's not a geometric sequence because the ratio is not consistent. This one has a ratio of 5. We just looked at that one. 5, negative 15, negative 60, 270. Negative 3, 6, negative 3. Ratio is not consistent. There was that negative 10, which you identified. And this is the arithmetic sequence. That was the first one we saw, was plus 8, plus 8, plus 8. All right. Great job. All right, we're right on top of that. All right, let's go back up here. Different forms, just like we saw with arithmetic sequences. We could have a list of terms. We could have it as a table. The first term is a 1. The second term is a 3. The third term is a 9. The fourth term is a 27. 1, 3, 9, 27. Or we could have it as a graph. The first term's a 1. Second term's a 3. Third term's a 9. Fourth term's a 27. So it becomes graphing these points. So we can see it in different ways, but we still should recognize, oh, that's a geometric sequence of numbers. And again, you will notice that there's not a continuous curve. We do not connect these with a line because it does not exist in between the 0.39 and 427. There's not a 3.2 term that is like 14.1 or anything. That does not exist. You can only graph just the points. Do not connect them. And again, just like last time, we're going to have a recursive and an explicit way to determine the terms. So recursive process requires knowing what the previous term is. Remember last time we had where you just take the term before it and you add the common difference. So this time we're going to say, like, if the common ratio was 4, you just say multiply by 4 to get the next number. So a recursive way to do that would say a sub n equals 4 times the number previous. So let's start making some notes on these different forms. So the recursive method. Remember, recursive is you have to know what the previous number was in the sequence. So recursive. If I want to know whichever term, I just take the common ratio and multiply it by the term before it. So if n is 10, I want to know the 10th term in this geometric sequence. I just find the common ratio and multiply it by the 10 minus 1, or the 9th term, a sub 9. And I can easily find out what that. So a sub n is the nth term. N is the number of terms. And R is the common ratio. Common ratio. So there's our first formula of the day right there, the recursive formula. So as long as we know what the term before it is, we just multiply it. Like when we were working earlier, we just multiplied the last number of the sequence times 4, or whatever the common ratio was, and that gave us the next one, right? So we just take the one ahead of it, multiply common ratio, and we can find the geometric sequence. Not too bad. Let's see, explicit formula. So an explicit formula allows to calculate any term directly. You don't have to know what the 9th term is to find the 10th term. An explicit formula is useful in ways that the recursive process would be boring. If we wanted to find the 27th term of a geometric sequence, like 8, 4, 2, etc., we could list every single term until we got to the 27th term, but who's got time for that, right? We don't want to have to list the first 26 terms in order to find the 27th. So that's where we can use an explicit formula and be much happier that we did. So we're going to learn how to derive the explicit formula. So let's see if we can't kind of build our little table here using this sequence of numbers. And the first term we know is 2. All right, nothing changes. The first term is always the first term. It's not going to change from being 2. The second term, how can we find the second term? Well, we take that 2 and we multiply it by the common ratio. What's the common ratio? 2 becomes -6, -6 becomes 18, 18 becomes -54. If we divide backwards, -6 divided by 2, we see the common ratio is -3. So if we multiply this times -3, we'll get the second term, -6, 2 times -3. So then if we want the third term, we can take 2 times -3, which is the second term, and multiply that times -3. So -6 was the second term. That's what that equaled. Times another -3 made it a positive 18. So this actually is 2 times -3 squared. Like, because -3 times -3 is -3 squared. So that means if we want the fourth term, we can take 2 times -3 times -3 times -3, or 2 times -3 to the third power. It's happening 3 times, and we get the -54. So that tells us that if we want the explicit formula, that could be a sub n. So if we want to find like the fourth term, we would take the first term, a sub 1, multiply it by the common ratio, raised to what power? Well, this was the third power when we went the fourth term. It was the second power when the third term. It was the first power when the second term. So raised to the power of n minus 1. If we want n, we raise this to the power of 1 less than that. We want fourth, we take it to the power of 1 less than 4. Where a sub 1 is the first term. We already defined r over here, and we know what a sub n is, and n is the number of terms. So this is our explicit formula. You've done it before. I know you can do it. So that is the two formulas we will use with geometric sequences. Recursive, when we already know the term before, or explicit, when we just want to jump straight to it. Jump straight to the term. So if we want to use this sequence here, and we want to find, let's say, like a 21st term. 21st term of the sequence right here. Well, we can keep with our table, 5th, 6th, 7th, 8th, 9th, and that's going to get real boring by the time we get down to about the 16th, 17th number. But if we use this formula, we take the first term, which was a 2, the common ratio, which was a -3, and n minus 1, since n is 21, -3 to the 20th power. So let's open up our calculator. Hello, calculator. There it is. Okay. 2 times -3 raised to the 20th power. Ooh, boy, the 21st term is pretty big on this. 6,973,568,802. And it's a positive. 20th term is positive. Which means the 21st term would be negative, right? Because we're multiplying by -3. So this is the 21st term. The 21st term is a positive. If we notice on this sequence, the first term is even, the third term is even, but the second and fourth is odd. So every even numbered term, the second and fourth and sixth and eighth and 10th, will be an odd negative number. But the odd terms, the first, the third, the fifth, the seventh, the 21st, are positive numbers. So that makes sense. That would be positive. That is the 21st term in that sequence. It gets pretty big. 6 billion. 6 billion right there. So they go through the same steps. 2 times the common ratio for the second term. 2 times the common ratio squared for the third term. 2 times the common ratio to the third power. -3 times -3 times -3 to get to -54. So the 2 comes from the first term. The -3 is the common ratio. The exponent is determined by 1 less the term number in the sequence. So the fifth term would be 162 by just continuing the pattern. And we have a little video where they show us the formula that we actually just figured out on our own on the paper there. So let's see their video on how they do this.
The fifth term of the geometric sequence is 162. 162 can be written as 2 times 81. 2 represents the first term in the sequence, which is indicated as a sub 1. 81 is the result of 162 divided by 2. 81 can be written as -3 to the fourth power, where -3 represents the common ratio between each term of the sequence. 4 is the result of the exponential equation 81 equals -3 to the power of x. Use the variable r to indicate the common ratio. 4 is the same as 5 minus 1. 5 represents the fifth term in the sequence, and 1 is the difference between 5 and 4. The variable n is used to represent the position of the term in the sequence.
All right, there is the formula that we've already got down in our notes for the explicit formula. To find a sub n, which n being whichever term you want to find, you take the first term in the sequence, multiply it by the common ratio raised to the power of n minus 1. Or again, n is the number of term that you're looking for. 6th term, 8th term, 21st term, whatever that is. So here they've repeated it, the geometric sequence formula. A sub n equals a to the first times r to the n minus 1. And we know what the variables are. We just defined those. So they can find the 11th term in this sequence. We found the 21st. They found the 11th to be 118,000. And again, since it's an odd number, it's an even answer. Right? Now you may be thinking that the geometric sequence looks remarkably like an exponential function. And you'd be correct, because it is got an 3 to the x there, like exponential function, 3 to the x when the x is in the exponent. And since we have a variable in the exponent right there, n is a variable, this is an exponential equation because it does have a variable in the exponent. Geometric series are used for events that are more static in nature, whereas exponential functions support continuous events. So this would have a value in between those. Geometric series, we only have the first term, second term, third term. It's not exactly exponential, because an exponential, we would connect all the dots and make a line. But like savings accounts, which earn interest, would be expressed as a exponential function if it got interest continuously. But if it just got interest like once a month or once a year or whatever, that would be a geometric series, because it would only get the interest in between month to month to month, not daily, continuously all the time. Here they put the two formulas together for us, which we have both of those in our notes already, the recursive and explicit forms of our equations. All right, page 4. Combination functions. The way to think of this is a sub 1 never changes. That's one part of our formula, right? It's a constant. Whatever the first term is will remain the first term as long as you're talking about that same sequence. First term is always the first term. What changes is r to the n minus 1. That's going to change based on which term you're looking for. Right? As you move through the terms, the value of r to the n minus 1 is going to change. That's going to change. If we multiply them together, that gives us our explicit formula. If you multiply the a times 1 times the r to the n minus 1, gives us a formula. Again, domain and range. Let's talk about that again. The domain, remember, we're talking about the term number is the domain. We do not have a 0th term. We do not have a negative third term. We do not have a 4.6 term. We only have first, second, third, fourth term. So the domain for geometric sequences is restricted to all integers greater than or equal to 1. Notice it has the word integers in there. That means there's no decimals. The domain is only 1, 2, 3, 4, 5, 6, just the term number. And that's true for all geometric sequences. All of them have a first term, a second term, a third term. Right? There's no in between first and second term. There's no 1.25 in the domain, because that would mean the 1.25 term. There's a line of people that say, hey, who's the 3.3 person in line? Well, there is no 3.3 person in line, Mr. Brock. There's a third person and a fourth person in line. That's correct. The range, could be anything, right? We saw a lot of different ranges on that sequence. We saw it where it was, 2, 6, 18, it just goes up the positive numbers. In geometric, we could have negative numbers, right? 6, negative 468,750. All those are the range. So the range will just vary by the sequence that you're looking at. The domain will not. It'll always be 1, 2, 3, 4, etc. All right, let's look at some examples. used in our formulas. So let's write this down because we need to figure out how to use these formulas to solve problems. Okay, I've got this problem written down. And we have two different formulas we can use. Let's see, this one, what they want to know, oh wait, I guess I should go back and see what they're looking at is the question. The 14th term. So we need the 14th term. A sub 14 equals what? So we know the first term, we know the 8th term, we need to know the 14th term. So if we want to know the 14th term with this formula, we just take the common ratio times the 13th term. Well, we don't know the 13th term. To find the 13th term, we need the common ratio times the 12th term. Well, we don't know the 12th term. So this is not looking very promising. So we need to go to this. This one, we can find the 14th term using the first term and the common ratio and n minus 1. We just need to know the common ratio. We do not know the common ratio right now because we know the first term and the 8th term. But since we have these numbers, we can plug them in here and find the common ratio. What is a sub n? Well, if we're looking at the 8th term, a sub n is negative 468,750. What's the first term? 6. Common ratio we don't know, but we do know n minus 1 because if this is the 8th term, this would be 7 since this is the 8th term. So let's solve for r. We have 6 times r to the 7th. So let's move the 6 to the other side by dividing. Let's get our calculator out. We don't have to do that by hand. That'll be pretty slow if we do that by hand. So let's move this over here. 468,750 negative. There's negative 468,750. Oh, I didn't mean to do that. Divided by 6 is negative 78,625. Oh, 125. I put 6. Same. All right, 125. And that equals r to the 7th. So if we take the 7th root, of those, that will equal our common ratio. So what is the 7th root? Let me hit shift where I can choose which root I want. That, the 7th root, negative 5. So our common ratio is negative 5. So now if we want the 14th, the first term times negative 5 to the 13th power. All right, 6 times negative 5, which is our common ratio, to the 13th power since we're looking for the 14th term. So let's plug that in. 6 times negative 5 raised to the 13th power. So the 14th term is negative 7,324,218,750. It's a big number, the 14th term, which we could have figured because it was already negative almost 500,000 at the 8th term. So it's negative 7 billion. So let's see what they get on their solution here. So they find r to be negative 5. They went through the same process we did, substituting what you know into the explicit formula, solving for r. And a to the 14th is negative 7 billion, 324 million, etc. So that is the same number we got. Great. Okay. Example 2. Is this the end of it? And yeah, here's our lesson summary. So we'll get into our series here in just a moment. A real estate developer is clearing 450 acres of land to build some commercial development. That's a big commercial development. 450 acres is a lot. Every day, half of the land is cleared, which means on the first day they did a whole lot of work, but then they only did half of that the next day and half of what's left the next day and half. So they're getting lazier and lazier. How many acres are left after 10 days? Round to the nearest hundredth. So first define each variable. What is the first term of the sequence a sub 1? That's 450 because that's what we started, right? 4, 5, no, 0. 450. Okay. What is the common ratio? It says enter a fraction by entering the numerator. So if it's clearing 1/2 each day, that's our common ratio. R is 1/2. Right, so jumping into Nigerian, so that is silent. So enter a fraction by entering the numerator. What is the value of the variable n? Well, they want to know after 10 days, so that would be the term we're looking for, the 10th. 10. Then you can apply the geometric sequence formula. How many acres are left after 10 days? So we gotta do the whole formula here. So let's write that down in notes before we get confused on that. So let's see. It was we need to know the 10th day, and the first was 450 times 1/2 to the 9th power. 450 1/2 to the 9th. So let's, oh, where's my calculator? There it is. 450 times, and I'll just do 0.5 because that is what 1/2 equals to the 9th power. So we got less than an acre, it looks like. We got 0.8. How much did it say rounded to the nearest hundredths? Nearest hundredths. So 88, 0.88. So we got 0.88. Yeah, that's what it equals. Less than an acre. They should be done with that in no time. All right, let's look at the lesson summary. All right, geometric sequence formula. Here's the recursive, here's the explicit. Domain, integers greater than or equal to 1, the counting, the natural numbers. Range is not restricted. It's restricted for each specific sequence, but as a rule, it could be anything. And the explicit equation is a combination of the constant a1 and the exponential function r to the n minus 1. There are some practice problems on page 5. Find the indicated term of the given sequence. Find the 10th term of the sequence 2, 8, 32. So you got to identify that common ratio, which would be obviously 4 in this case. 2 times 4 is 8. 8 times 4 is 32. Use our explicit formula. A sub n equals 2 times 4 to the 9th. 2 times 4 to the 9th. See which answer you get? There's 5 problems right there. All right, let's look at our assignment for this first lesson. Find this 16th term. They give you the 1st and the 8th. So in that case, you're going to need to do what we did here when you have the 1st and the 8th. Figure out what the common ratio is, then use the formula to find the 16th term. Identify the 19th term where you have the 1st and the 9th. It says round to the nearest hundredth. So the common ratio is not going to be an integer. It sounds like. The common ratio is going to be a decimal. Well, certainly if it's 358.8, there's a decimal involved. So you need to round that to the nearest hundredth. A bacteria culture begins with 13 bacteria that triples at the end of every hour. How many are grown during the 10th hour? So you just find in the 10th term, common ratio is 3. First term is 13. There you go. Get in the functions 500, f of n equals 500, g of n equals 9/10 to n minus 1. Combine those, solve for the 11th term. Okay, so you can eliminate 2 answers immediately. Actually, you should be able to eliminate all the answers except for 1. Just looking at combining those 2 equations. And create the explicit formula and list any restrictions by looking at this table. Looking at the domain, you should be able to eliminate two of those right away. Would the domain be n is greater than or equal to 1? Or would it be n is greater than or equal to -4? And it should say the word integers in there. It's not just greater than or equal to 1. So, all right. That is our first lesson and assignment for the week. Let's look at geometric series, very similar to last week. Remember, a series is where we're adding the numbers together. We got a sequence of numbers, and we're going to add them together. Oh, and we got a little video, a little airplane. This looks like it could be kind of good. Most of these videos are kind of goofy, in my opinion, but they do bring the math point across. They're just kind of goofy cartoons. All right, let's see.
Rachel's mother just returned from a vacation to Moscow. She brought back a set of matryoshka, or nesting dolls, for Rachel. Nesting dolls are a series of dolls that open up so that each doll contains a smaller doll until you get to the smallest, innermost doll. The packaging that came with the dolls notes that there are 8 dolls and each doll is 10% smaller than the previous one. Rachel has a 2-foot long shelf in her room, but it's covered in small dolls already. She doesn't want to clear it unless she knows the nesting dolls will fit. First, she measures the largest doll. At its widest, it is 5 inches long. Rachel does not want to find 90% of 5 inches, then 90% of that number, and so on 8 times over. So instead, she uses a special way of adding numbers that change by a constant percent. The first doll is 5 inches wide. The next doll is 5 inches times 0.9 because it is 10% smaller. The next doll is 5 inches times 0.9 squared because it is 10% smaller than the previous doll. Rachel can find all of the doll's widths this way. She knows that when a number is multiplied repeatedly by the same constant, the sequence of products is called a geometric sequence. In this lesson, you will see how to add terms quickly in a geometric sequence. This sum is called a geometric series. You can use it to see if the nesting dolls will fit on Rachel's shelf. You find the sum of a geometric series using the formula S sub n equals a sub 1 minus a sub n times r all over 1 minus r. S sub n is the sum up to the nth term. In this case, you want 8 terms added. A sub 1 is the first term, and a sub n is the last term. So here, a sub 1 is 5, and a sub n is 5 times 0.9 to the 7th power. R stands for the common ratio and is the factor that each term is multiplied by. In this case, r is 0.9. So substitute and solve. The dolls will span about 28.5 inches, or just over 2 feet and 4 inches. Rachel's 2-foot shelf is not enough.
Let's see. I'm just looking at their formula. They put the formula here. S sub n equals a1 minus a sub n to the power times r over 1 minus r. So this is our formula. I'm going to put that in our notes. Put what they gave us as our first formula. Find a series a1 minus a sub n times r over 1 minus r. So this is a little more complicated than our arithmetic series formula. So that's what they gave us in this right here. I was looking at is when they substitute 5 because that's the first doll. And for a sub n, they substituted 5 times 0.9 to the 7th because they're trying to find what the 8th doll is. That was looking back at our explicit formula. 5 is the first term times the common ratio times n minus 1. So this is the explicit formula for finding the 8th term. times r over 1 minus r. So, and the r was 0.9. So all of that going to go together to tell them that it's 28.5 inches. And her shelf is 2 feet long. So that it didn't quite work. I will say Rachel is even more of a math nerd than I am, because I would have laid all the dolls out and got a tape measure. Right. Oh, yep, ain't going to fit on 2 feet. But, she wants to do it mathematically. She's going to do the math at 0.9 each time and do that. Although I think she could still use the shelf, because when you got the little dolls, she could put them in front and back. She could stagger them, and I think they would all fit. But she's obviously like very ADD about, ADHD. She's very picky about how everything's going to sit in her shelf. It has to be exactly straight. So it doesn't work for her. But we're going to learn, how do geometric sequences and series differ from each other, and what information must be included to find the sum of a geometric series. All right, another activity. Let's look and make sure we can identify these just like we did with the others. Put each list of numbers in the category which it belongs. We have a list of numbers. It's either a geometric sequence or it's a geometric series. Remember, series are added together. Sequence is just a list of numbers. Series are added together. These are just a sequence. So 1, 5, 25. Is that a sequence or a series? You can just put U or R if you want for sequence or series. But which is it? 1, 5, 25. Sequence or series. Okay. A sequence is just a list of numbers. A series is when we add that list of numbers together. A series is when we add those numbers together, which means you can tell the difference by looking at the numbers. Does it have a comma or does it have a plus sign? Are we adding them or are we just listing them? So that kind of tells us this first one. This is not adding them together. It just gives us the numbers. So this first one is a geometric sequence. Right? It tells us the numbers 1, 5, 25. It does not tell us to add them together. So now let's look at the second one. 4, negative 32, 256. Yeah, Q. That's sequence, you think? Q. R's would be series. Q would be a sequence. 4, comma, negative 32, comma. Yeah, it's just listing a sequence of numbers together. Oh, here we go. 4 plus 6 plus 12. Now you see the difference now? Now you can get a clearer picture of what we're doing here. With a geometric series, this is just a sequence of numbers, 3, 6, 12. It's times 2 every time. But we're going to go ahead and add them together. We're going to add them together. Oh, don't let this one confuse you. 9 minus 27 plus 81. So Mr. Brock, you said we're going to add them together if it's a series. Well, we are. We're adding negative 27. And when you add a negative number, you just subtract, right? So there you go. Great job. 1, 5, 25 is a sequence. The terms are written as a list separated by commas. Second one also separated commas. When it's a sequence, we are adding the terms together. All right. Great job. Got to get that clarified so we know for sure what we're doing. Page 2. When given a geometric sequence with a set of numbers, it's possible to use the geometric series formulas to find them. So let's try it out on these examples. So find the sum of 5, negative 15, 45 if there are 11 terms. All right, let's put this down. 5, negative 15, and 45, 11 terms. So first we have to identify what's the common ratio, because we got to use that common ratio in our formulas. 5 to negative 15 to positive 45. So our common ratio is negative 3. All right, we can see that. 5 times negative 3, negative 15 times negative 3. So if we want to find the 11th term, our formula says take the first term, which is 5, and multiply it by the 10th term times negative 3, because that's, a sub n. Oh, that is the 11th term, sorry. Not a sub 10. A sub 11. First term minus the 11th term times negative 3 over 1 minus negative 3. Now here's the problem, though. With our formula, we don't know the 11th term. We know the first, second, and third term. So let's look over here, our explicit formula. Let's say if we substitute 5 minus, instead of a sub 11 would be the first term times the ratio n minus 1. The first term times the common ratio to the 10th power times negative 3. Because we got to take it times the ratio again. All right, all of that over 1 minus negative 3 would be 1 plus 3. So over 4. So let's get our calculator and do some math here to simplify this down as best we can. So the first thing we do would be the exponent. Negative 3 raised to the 10th power. So this would become 5 minus 5 times 59,049 times negative 3 over 4. See, we just took the exponent and simplified it to this number. Now we need to do the multiplication before we do this, because that's a sequence of operations, right? Times 59049 times negative 3. So it's 5 minus this. Five minus negative 885,735 all over 4. Okay, 5 minus 88573. Oh, 885,735 minus. So 5 minus this negative would be positive 885,740, because subtracting a negative, and divide it by 4. So it looks like the 11th term would be 221,435 as a positive number. Well, does that make sense? That would be a positive number. The first term is positive. The third term is positive. So it looks like all the odd terms are positive. The even terms, the second, the fourth, all those would be negative. So since the 11th is a odd number term, it should be a positive number. So this is probably right. 221,435. Let's see what they got is their answer here. 221,435. Absolutely correct. There are 11 terms. So example 2. They have a video for this one. Find the sum of an 8-term geometric sequence. So they give us the first term and the last term, and they want to know for 8 terms. So let's, again,
No matter which formula you use, you will need to know what the common ratio is in this series. To find this unknown value, you will use the geometric sequence formula a sub n equals a sub 1 times r to the power of n minus 1. First, define each variable. There are 8 terms in the sequence, so n equals 8. The first term is 7, making a sub 1 equal to 7. Finally, the last term is 114,688. Use this number for a sub n. Simplify. Now that you know the value of the common ratio, you may use either formula to find the sum of the series. However, to ensure that you have practice working with both formulas, let's use the formula S sub n equals a sub 1 minus a sub n times r all over 1 minus r. The sum of an 8-term geometric sequence, if the first term is 7 and the last term is 114,688, is 152,915.
Okay, they're talking about two different formulas, but they haven't given us a second formula actually officially yet. We don't have one on our notes, so we need to derive our second formula as well. So, and they have a third one there. Okay, this has the two formulas. So let's write the other one down in our notes as well. I'll put it and switch over there. This would be our second formula, because right here, when we were solving this problem, a sub 11 would have been a sub n, right? But we didn't know a sub 11, so we had to substitute in this that we had in the first lesson, in the first part of the class, 5 times negative 3 to the 10th. Well, 5 times negative 3 to the 10th times another negative 3 means this is negative 3 to the 11th. So we were finding s to the 11th. So we can rewrite this way to where if we know the 11th term of an 11-term series, we could use this formula. If we don't, look, this just uses the first term twice. First term, common ratio, n. We don't have to know the last term in the series. This one, we have to know the last term. If we want the sum of the first 20 terms, we need to know the first and the 20th term. If we want to know the sum of the 20th term here, we only have to know the first term and the common ratio. So these are the two geometric series equations, formulas, whatever you like to call them, that you need in your notes that we can use to solve all of these. So look at this. It says answer the following questions. Which geometric series or formula will you use? It says research states that viewership for the Summer Olympics increases 22% every 4 years. There were 1.5 million viewers in 1980. And if the percentage stays consistent, how many million viewers were there total from 1980 to 2008? Well, we don't know how many viewers there were in 2008. So we don't know the last term in the series. So we should use this formula that only uses a sub 1. Yeah, we don't know how many viewers, but we know the a sub 1 is and the percentage. So we can use that formula. All right. And it's got more problems there. Matching in a sub 1 and r for this 1.5 million. That was the first year. 22%, that was the amount of increase each time. So that would be our R. And we're looking at 8 Olympics between 1990 or 1980 and 2008. That would be 8 different Olympics. So, all right. Instead of using the formula A sub 1, you'll use A sub 1, 1 plus R. Oh, this gives a whole different thing. A small change must be made because the common ratio is a percentage. So this is saying you can't just use the 22% because that only tells you the amount of increase each time. So if you're actually trying to figure out how many viewers, you would have to add 1 to that 22%, 1 plus R, 1.22% to know how much is each time. That's only just you have to make that because it's talking about a percentage increase, not giving you the term. So common ratio is a percentage. You got to make that add 1 when the common ratio is a percentage. If the percentage is decreasing, it'll be subtracted from 1. So we probably need that in our notes. When R is a percentage. Okay, when R is a percentage, we got to change this to S of n equals A1 minus A1, 1 plus R to the n over 1 minus 1 plus R. If R is a negative percentage, if it's going down, you just use a minus R because it's a negative. 1 plus a negative R. You subtract. So that is the big key thing. When R is a percentage of increase or decrease. So that's a good note to have when we're dealing with anything that is a percentage change. Good note. And it says we can apply it. Okay, that's that. Just go ahead and finish that problem. I'll leave that if you want to go through because it'll tell you if you're correct or not. How many million viewers did it? Solve it. Solve that problem. Application. Sebastian purchased a mega bouncy ball. Oh, we love the mega bouncy balls. It says it bounces up 83% of its original height. So if you drop it from 10 feet, it'll bounce back up to 8.3 feet. Sebastian sets up a yardstick and drops it from 3 feet and compiled his list. So he dropped it from 3 feet and it bounced back up to 2.49 feet, which means he's really good with that yardstick. I would not be able to tell 0.49 of a foot. And then the next time it bounced up at 2.07, the next time it bounced back at 1.72. And let's say you're going to let it fall 12 more times to where it's hard to measure accurately because it's bouncing such a small amount. So the total distance it dropped, first it dropped 3, then it dropped 5.49, and then 7.56 when we add all 3 of those together and keep going. He's going to use a geometric series. So he dropped it 16 times altogether. Well, it bounced, 16 drops. So he can use this A sub 1 minus A sub 1 R to the n. Using the information he knows, that it comes back up 0.83%. It's going to drop a total of 16.75 feet over the 16 times that it fell. Here's our lesson summary. Here are the 2 formulas we used. It just doesn't have the one where you substitute with the percentage, but A sub 1 minus A sub 1 R to the n over 1 minus R. That's the one you use if you do not know the last term. Or if you do know the last term, A sub 1 minus A sub n times R over 1 minus R. There are 2 pages of practice problems for this one. Match terms. Which one of these? Oh, this is a good one. I'm going to blow this up. We want to look at this pretty close. Which one of these is the arithmetic sequence formula? Which one of these is the arithmetic series? Which one of these is the geometric sequence? Which one of these is the geometric series? These are all the formulas that we wrote down last week and this week to determine our arithmetic sequences and geometric sequences and series. So when you look at these and you're trying to match them up, the easiest way to divide them is, wait a minute, which ones use the common ratio? This has an R and this has an R. So these two must be geometric. And remember, when we deal with a series, it's not A sub n, it's S sub n, because we're taking this sum, we're adding them all together. So this S sub n must be series. And since there's an R in the formula, it must be the geometric series. If I click geometric series and that, they disappear. This is the geometric sequence. The only other one that uses an R is right there. That leaves the arithmetic sequence, arithmetic series. One of these is A sub n, where it adds n minus 1 times d to the previous one. The other one is S for sum, for adding together. Sum is series. Sequence is that one. That's good. So you can go do that if you're not sure if you know which is which. Hit begin and see if you can match all those up. All right, and then this matches. Oh, and this is a description. Match the sequence of series described on the left with the formula that's most appropriate to evaluate it. This is find the 40th term of 3, 6, and 12. Let me make this big again because this is some good information here. Find the 40th term of 3, 6, and 12. Well, 3 to 6 is b plus 3, but then it goes to 12. So this is not arithmetic. 3 times 2, 6 times 2. This is geometric. And am I finding the total? No, I'm just finding the 40th term. So I need a geometric sequence formula that does not use the 40th term because I don't know what the 40th term is. So this is a series, this is a series, this is a series, this is a sequence, this is a sequence, this is a series because of the A and the S. So it has to be one of these two. This one uses D, which is common difference. That's arithmetic. This one uses R, which is ratio. So I must use this one to find the geometric sequence. Look, this is find the sum. 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 This is just find the 6th term. So that would be the other one. That is an A sub n. The 6th term would be the first term plus 5 times the common difference. That one. These are all finding the sum. So these are all S sub n's. Find the sum of the first 4 terms of a series. First term is 1, 4th term of 7, common difference of 2. So we know the first term, the last term, and the common difference. A sub 1 minus A sub n times R. That's common ratio. That's not common difference. Number of terms divided by 2, first plus last. Oh, we know 4 terms. First plus last. Do we need the common difference? A sub 1 plus, this is an R. That is not common difference. That's a geometric. That's a ratio. And this uses 2 times the first term minus n minus 1 times d. This doesn't even use the last term. So since we know first term and last term, must be that one. The sum of the first 100 terms of 1 plus 3 plus 5 plus 7. Look, that's arithmetic. It's adding 2 every term. 1 plus 2, 3 plus 2, 5 plus 2. So this would be the common difference. These are both ratios. So here we have one, A sub 1 minus A sub n. So this knows the last term. This uses A sub 1 all the way. So this one knows the last term. This one doesn't. Find the sum of the first 100 terms of 2 plus 4 plus 8 plus 16. This does not know the last term. So it would use this one, which by process of elimination must be that one. All right. That's good practice. If you're not a little confused on these formulas, go to page 3, try that out. Page 4 has some actual solving. What is the sum of this sequence? If there are 10 terms. Figure out which of the 2 formulas you need. You do not know the 10th term, so you should use your one written on the right. Here's how it works. There's 5 questions here. 5 questions. All right, our second assignment for the week. Find the sum of this geometric sequence. 9 terms. That's a geometric series. Find the sum of 9 terms. Find the sum of an 8 term. And the first term is 7, and the 8th term is right here. So you know the first term and the last term. So you can use that formula that has the first term and last term. Evaluate S5, so the 5th term for this sequence. This doesn't say the sum, it just says what is the 5th term. So what is the 5th term of that sequence? Christina Badayoyo says that every time it'll be 70% of the original length. So you drop it and it'll come back up 70%. She sets up a tape measure and throws it 3 times and charts the first 3 terms of how high it comes up. What's to know after 10 times? How high is it? What's the sum? Add them together. Well, you know the sum is at least 6.57 because that's what the first 3 added together equal. So you can rule out 2 answers right there. The sum. And here is the diameter of a bacteria colony. It doubles every hour as represented by this graph. So at the beginning, it has a diameter of 1. After 1 hour, it has a diameter of 2. After 2 hours, it has a diameter of 4. After 3 hours, it has a diameter of 8. What is the diameter after 9 hours? That's off the chart, but you can calculate that. 5 questions. 5 questions for each assignment. So there you go. Geometric sequence, geometric series. Next week, we'll look at graphing those, which won't be too particularly hard, but this is a good start for this week. So, all right, guys, if you have any questions, hang around. You got about 10 minutes left before advisory. If you want to get started on either one of these, maybe I'll get one or both of them done. Advisory doesn't start till 10:38, so you got like 15 minutes. So, all right, guys, have a great week. We'll see you next time. And hang around if you got questions.